So please wait for 5 minutes. I will start the session. Please wait for 5 minutes. I will start the session. Good morning, Kavananda. Good morning. So please kindly tell me, is it the audio, video, and screen? Is it okay? Please kindly tell me. Audio, video, and screen. Is it okay? Yeah. Good. So let's continue with the previous class. So we are discussing about system stability point of view. So at which point the system is stable, which point the system is stable, that type of things we are discussing here, right? So with respect to dp by d delta, dp by d delta. See, we said this delta equals to beta, which was the stability angle, below which the system will be stable, above which the system will be unstable. For example, I'll tell you, just look here. So this is one transmission line where we have transmission line wire having a angular parameter b, so-called beta, something like 75 degree. Beta value I am saying as 75 degree here. Yeah, 75 degrees we have beta. So how much is that angle delta we have to maintain now? How much is that angle delta we have to maintain? Tell me please. How much is that delta we have to maintain? Can we go for 73 degree? Because we said delta less than beta system is stable now. Delta less than beta system is stable. Can we maintain this delta equals to 73 degree? Yeah. See, for example, delta equals to 73 degree, system is stable. That's okay. But you observe that this delta is very close to beta. Na? Delta is very close to beta. For example, if you see in this diagram, this is 75 degree. This point is 75 degree, and 73 degree might be here. 73 degree might be here. Then how is the power flow in the line? Very close to P maximum. Power flow is very, very close to P maximum. Then definitely the system may lose the stability if there is an increment in the power demand. If there is an increment in the power demand, definitely the system is going to lose the synchronism. Okay, yeah. So let's see. So 73 degree may not be suggestible because if there is a small increment in the power demand, system will be definitely losing its synchronism. Right. So how much is the delta we have to maintain now? A bit very low compared to beta, let us say. For example, delta, can I maintain 60 degree? Delta, can I maintain 60 degree? Yes or no? Yes. If you maintain delta equals to 60 degree, maybe in this graph you see. This is 60 degree location, na? 60 degree. With respect to 60 degree, these are power flow. We have a good margin, good gap between P maximum and present flow. Between P maximum and present flow, there is a good gap. Okay. So system is well stable for small disturbances. System is well stable for small disturbances. But if there is a big disturbance, if there is a large disturbance on the system, then definitely system will be losing the synchronism. System will be losing the synchronism. All of you getting my point? All of you getting my point? Please tell me. Delta equals to 60 degree if you are maintaining. System is stable for small disturbances. System is stable for small disturbances. That's okay. But if there is a big disturbance, definitely the system will be losing the synchronism. In that view, I can't maintain delta equals to 60 degree also. I can't maintain delta equals to 60 degree also. Then how much you have to maintain? See, actually, what's your aim here? What's your aim? See, we have to set our initial operating point in such a way that the system does not lose the synchronism even for a small disturbance or a big disturbance. For any type of disturbance, the system should not lose the synchronism such that we have to set the value of delta. So in that view, generally we prefer to take this delta in the range of 30 degree to 45 degrees. 30 degree to 45 degrees. These are going to be called generally as preferable operating angles of the system. These are going to be called as preferable operating angles of the system. Preferable operating angles of the system. Okay. 30 to 45 degrees are going to be called as preferable operating angles. See, if the delta is below 30 degrees, system will be even more stable, right? See, if you are maintaining the delta as low as possible, system stability will be very, very high. System stability will be very, very high. Okay. Now the thing is delta less than 30 degree, then also the system will be even more stable. System will be more stable. But we are preferring in between 30 to 45. Why it is so means to have a good amount of power flow, as well as good stability for the system, right? So in bracket, right, have good amount of power flow, and good stability for the system. Good stability for the system. Good stability for the system. You can say the delta equals to 30 to 45 degrees is taken. Is that voice is okay? Is that voice okay? Please tell me. 60% why we are not preferring means because if there is a large disturbance, there is a chance of instability. There is a chance of instability for a large disturbance. That's why we can say we are not preferred to take for what we call 60 degrees. Yeah. Okay. So let's continue. So till this point we have discussed about the what we call exact power equations, and we have discussed the conditions with respect to exact power equations only. Now we are going to some sort of approximate power equations. In the next slide. Approximate power equations. Approximate power equations. Maximum power value is a constant, Bhaskar. Maximum power transfer capacity of the system, it's a constant number. Maximum power transfer capacity of a system is a constant number. According to the present operating condition, power flow is going to be differed from one to the other. Okay? Yeah. Since for easiness in analysis, we are going for these approximate equations. Look here. Generally, for extra high voltage lines and ultra high voltage lines, extra high voltage and ultra high voltage like 220 kV, 400 kV, 765 kV, for these levels, the XPR ratio is very, very large. For EHV and UHV lines, XPR ratio is very high. See, if that XPR ratio is very, very high, you are saying, then obviously reactance is very, very large compared to resistance value. Else, we can say simply resistance can be neglected in the series combination. That implies or can be neglected. Next. Look here. Okay, so just I am moving on to the power equation for time being. Real power equation. Let me copy that. Power equation once. Yeah. So this is a real power equation. Just check this. Real power equation. I'm copying that. Yeah. See this. See, already we are saying XPR ratio of the system is very large. Just now we said. So if that's the case, how is this beta? How is that beta angle? Anybody please tell me. How is that beta angle? That will be very close to 90 degrees. So beta will be very close to 90 degrees. Okay. Close to 90. How is alpha? How is alpha? Alpha. Alpha is angle of A, na? Alpha is angle of A very close to 0 most of the times, like 0.5 degree, 0.6 degree, like that we are going to experience near to 0, near to 0. Then obviously this beta minus alpha close to 90, beta minus alpha will be close to 90, cos 90 in the sense it will be 0, cos 90 in the sense it will be 0. So this second term will vanish completely. Second term will vanish completely. We left with only the first term. We left with only the first term here. Okay, what is that first term we have? Mod Vs, mod Vr by mod B, cos of beta minus delta. Mod Vs, mod Vr by mod B, cos of beta minus delta. Okay, listen now. I'm asking one very simple question. Very simple question. Just look at this. Which transmission line parameter? Which transmission line parameter decides the real power flow? Or on which transmission line parameter real power flow will be depending? On which transmission line parameter real power flow will be depending? Beta. Sorry, B. B. Parameter B. Yes or no? Line parameter I am asking. Line parameter. Line parameter is obviously B. Okay, next thing. Next. What do you mean by the parameter B? What do you mean by the parameter B? That B is nothing but series impedance of line. B is nothing but the series impedance of line. Now, what I was interested to tell you here is, real power flow mainly depends upon the parameter B. Real power flow mainly depends on the parameter B, right? So, as it is depending on the parameter B or series impedance, can we neglect the effect of the shunt admittance here? Can we neglect the effect of shunt admittance? Yes or no? Yes or no? Yes. So we can neglect the effect of the shunt admittance while we are going for the power equations further. That's the second assumption what we are going to make. So I can say here, PR mainly depends on parameter B or series impedance Z. Series impedance Z. So the effect of shunt admittance can be neglected. Admittance can be neglected. The effect of the shunt admittance can be neglected. Effect of shunt admittance can be neglected. See, after neglecting that shunt admittance and after neglecting that series resistance, what that network is consisting now? Only series reactance it will be consisting. So I can say the network will be consisting only series reactance. So this is the approximate model of the transmission. Approximate model, we can say like this. And this is the sending end side. We have mod Vs at an angle delta. And this was the receiving end side. I can say mod Vr at an angle 0. And this is Jx. You can call it is x at an angle 90 degrees. Jx in the sense, you can say x at an angle 90 degrees. 90 degrees. Okay. So now simply what you do is, you find out ABCD parameters of this. Simply you substitute these ABCD into the power equations. So that we can get the approximate real power and reactive power expressions. Okay. Yeah. What are the ABCD of this model? So, for example, if you feel this is a series impedance Z, so it will be 1Z01 ABCD. A 1 at an angle 0 degree. Parameter B x at an angle 90 degree. Parameter C 0. Parameter D 1 at an angle 0. 1 at an angle 0 degrees. Clear? 1 at an angle 0 degrees. Now, after getting this ABCD, now I will go with the real power equation PR. Real power equation PR, I can say. Let's see this. This is the real power equation PR. real power equation here. See, what is this beta we can keep? 90 degrees. Beta we are going to keep it as 90 degrees. And what is mod B? X. Mod B value we are going to keep it as X. And mod A 1, mod B X. 1 X. Mod VR square cos beta. Beta 90 degree, alpha 0 degree. Beta 90 degree, alpha will be 0 degree. So cos 90, 0. So this term is 0. So this PR will come to be mod Vs into mod Vr by X into cos of 90 minus delta means it will be sin delta. Cos of 90 minus delta means it will be sin delta. Mod Vs mod Vr by X into sin delta we can say. Sin delta. It's a approximate real power equation. Approximate real power equation. Approximate real power equation. Next thing, approximate reactive power by using the same conditions. I can say in the next slide. Approximate reactive power equation. Reactive power equation. Okay. So let me copy that reactive power equation. This one QR equation we have. Yeah. See this quickly. Write this one. This is a very, very important one with respect to examination. These things what I am discussing. So I can say this beta is 90 degree here, 90 degree, and B we are going to replace with X. B we are going to replace with X here, and mod A mod B values 1 X. You can say mod A is 1 and B is X. Mod VR square. Sin beta minus alpha means it will be 90 minus 0. So sin 90 that will be 1. So the approximate QR will come to be Vs into Vr by X into sin 90 minus delta, it is cos delta minus mod Vr square by X into sin 90, that is 1. Sin 90, that will be 1. Sin 90. So you can take that Vr by X common or Vr by X. You can take common and you will get now mod Vs into cos delta minus mod Vr. Mod Vs into cos delta minus mod Vr. So this is that QR expression. QR, approximate QR expression. Approximate reactive power equation. Okay. Now, next, what is the condition for maximum real power transfer? What is the condition for the maximum real power transfer? Again, you should say dPr by d delta is equal 0. dPr by d delta equals 0. By using that, you will get a condition like delta equals to 90 degree. Delta equals to 90 degree. Let's say quickly. Condition for maximum real power transfer. Condition for maximum real power transfer, PR maximum. So you have to call this dPr by d delta value is equals to 0. That's a condition. If you take up the dPr by d delta, you get like Vs into Vr by X. Sin delta differentiation will be cos delta. That is 0. So that Vs Vr by X you take to the other side. That will be 0. Cos delta equals to 0 is a condition. Cos delta equals to 0 is a condition. Then how much is delta? You can say 90 degrees. Delta we are going to call it as 90 degrees. Delta equals to 90 degrees. That's the condition for maximum power transfer capacity. Sometimes the maximum power transfer capacity is also going to be called as steady state stability limit, or you can say steady state power limit. Steady state power limit. Steady state power limit. We discussed it in the stability. We discussed it in the stability analysis. Okay, let's give the delta equals to 90 in the PR equation. Let's give the delta equals 90 in the PR equation. So you get sin 90. That will be 1. So what's the maximum real power transfer now? Mod Vs into mod Vr by X we can say. So I can call here maximum real power transfer value. Power transfer value. So you can say PR max is equal to the value of PR by keeping the delta is equals to 90 degrees, which is nothing but mod Vs into mod Vr by X. PR maximum is equal to mod Vs into mod Vr by X. This is what we call as steady state stability limit. Steady state stability limit of the system. Okay. So let's see in the next slide. How is the value of reactive power at this condition of PR max? How is the value of this QR value at the condition of the PR max? Means you should keep delta equals 90 in this. Delta equals 90. And if you take cos 90, that will be 0. So first term will vanish. And you will get only here minus mod VR square by X. That's the reactive power QR. So I can say QR value during PR maximum condition. During PR maximum condition. QR value during PR maximum condition. So QR by keeping delta equals to 90 degree will come like minus mod VR square by reactance. We're getting as minus mod VR square by reactance. Cos 90, first term is 0 and you get here minus mod VR square by X. QR value. Next thing. See, the same comment what we have made earlier, we are going to repeat now. Same comment what we have done earlier, that we are going to repeat here. See, QR is negative during PR maximum condition. QR value was negative during the PR maximum condition. All of you getting this? Right. See, whenever the QR is negative during PR maximum condition, QR is negative during PR maximum condition. PR maximum condition. Now, what you can say from this? What you can say from this? QR is negative means what? The load what we are keeping at the receiving end side is absorbing negative reactive power. Load is absorbing negative reactive power means whether the load is absorbing the reactive power or delivering reactive power, you can say. Delivering the reactive power. Following. So load must have a capability of delivering the reactive power, we can write. Load must have a capability of delivering the reactive power. Delivering reactive power. Load must have a capability of delivering the reactive power. That implies load must be capacitive in nature. Load must be capacitive in nature. Capacitive in nature. Okay, now let's go with power angle curve. Power angle curve, PR versus delta. So already we have written here PR is equals to Vs VR by X into sine delta, so called P max into sine delta. So we know power equation here, power equation. PR is equals to simply P max into sine delta. Will it pass through origin? Will this curve passes through origin in the PR versus delta? Yes, definitely. We have only sinusoidal curve. Sinusoidal curve means obviously it passes through origin. So let's show that X and Y axis first. So this is a delta axis I am showing, and it was a power axis. Okay. So power axis, and this was of delta axis. And I will show that power angle curve. Something like this. You can say the power angle curve passing through origin. and this is the maximum power transfer capacity of the system. Maximum power transfer capacity of system. And this is a point of 90 degrees. That's the point of 90 degrees. 90 degrees. Okay, next thing. Just have a look here. See, when the system is stable and when it is unstable, that's what the points we have discussed earlier also. These points already we have discussed, but still I am saying you. If the operating point lies in the positive slope region, operating point lies in the positive slope region of the power angle curve, then we can say the system is stable. So I can say, particularly in this zone, you can observe that dPr by d delta is positive. In this zone, you can say that dPr by d delta was positive, and we can say the system is stable in that zone. System is stable. So in other region, so-called negative slope region, we have something like this. dPr by d delta less than 0. dPr by d delta value less than 0. In this region, the system will be unstable. System will be unstable in the negative slope region. Of course, if you want to say the angles, delta less than 90 degree, it will be stable. Delta greater than 90 degree, it will be unstable. Delta less than 90 stable, delta greater than 90 unstable. And you know, this is a point at which you have dPr by d delta is equals to 0, and that point angle is 90. The point angle is 90. At that point, the system is either marginally stable or you can say marginally unstable. At this point, system is either marginally stable or marginally unstable. Marginally stable, or you can call this marginally unstable. Marginally stable, or you can say this is marginally unstable. Clear? Okay, yeah. Next thing. Obviously, the delta equals to 90 degree, what we have now, it is going to be called as stability angle of the system. Stability angle of the system. And what are the preferable operating angles now? What are the preferable operating angles? 30 degree to 45 degree. 30 to 45 degree, same as the earlier discussion we have done today. Delta in the range of 30 degree to 45 degree. These are going to be called as preferable operating angles. Preferable operating angles. Preferable operating angles. Okay. Next. So next thing, let's take up some problems on this one. Some problems on this. First problem I'm going to take up. Yeah. So you see this one. See this question. Go through it quickly. So it's from our workbook only. The ABCD constants of a nominal pi network representing a three-phase transmission line. ABCD constants of a nominal pi network representing a three-phase transmission line are A equal to D 0.95 at an angle 1.27 degree, B 92.4 at an angle 76.87 degree, C 0.0006 at an angle of 90 degrees. Find the steady state power limit means Pmax. Steady state power limit means you have to get the Pmax. if the sending end and receiving end voltages are maintained at 138 kV, sending end voltage maintained at 138, receiving end voltage also maintained at 138, and the series resistance and shunt admittances are neglected. Series resistance and shunt admittances are neglected. Let's write first. See, he is saying that in this way, we have a transmission line outside, practically speaking. Transmission line. That transmission line, what we are seeing on the tower, represented in the nominal pi. Transmission line represented in the nominal pi. Okay. So, nominal pi model ABCD parameters they have given. Nominal pi model ABCD parameters. A value, how much? How much he's saying? 0.95 at an angle 1.27 degrees. Parameter B, it will be 76.8, sir, 92.4 at an angle 76.87 degrees. Parameter C, 0.0006 at an angle of 90 degrees. Okay, done. Next, look here. Sending end and receiving end voltages are maintained at 138 kV means sending end voltage magnitude, receiving end voltage magnitude, both are equal to 138 kV line to line. Both are equal to 138 kV line to line. Okay, and he's asking to find steady state power limit, means P maximum. He's asking to find the value of P maximum. How much is the value of P maximum? Steady state power limit. If sending it, okay, series resistance and shunt admittance are neglected. Series resistance, shunt admittances are neglected. Series resistance and shunt admittance are neglected. Okay, see, listen. See, series resistance and shunt admittance are neglected. After neglecting these two, what is Pmax equation? What is the equation for the P maximum after neglecting the series resistance and shunt admittances? Tell me please, what is that? That is nothing but VSVR by X, na? That's what we have studied just now. The same assumptions we have made just now. So, maximum power transfer capacity after neglecting the resistance and reactance values will be Vs into Vr by X, you can see. What are the values of Vs and Vr? 138. See, listen kindly. If you want to get the three-phase power, you can keep directly line-to-line voltages. Because P maximum per phase equals to Vs phase into Vr phase by X. P maximum three-phase multiplied with 3. So you get 3 Vs phase, Vr phase. 3 Vs phase, Vr phase is nothing but Vs line to line, Vr line to line, and this is a P maximum three-phase. Okay, so I'll substitute that. What is the X value? That's the thing we have to do. Vs, Vr, they have given 138. What is X value? See, for that X value only, he said some data. See, particularly, listen all of you. Listen. In case of nominal pi model, what is parameter B? What is a parameter B in case of nominal pi? Parameter B in case of nominal pi is what? Anybody? That is nothing but series impedance Z. See, by giving the nominal pi network ABCD parameters, his interest is to tell you parameter Z, series impedance of transmission line itself is a number 92.4 at angle 76.87 degree. From that, you take real part, imaginary part. That imaginary part will be series reactance of line to be taken up in the calculation. Okay, so I'll write in nominal pi, B is equals to Z, we can say. Therefore, Z value will be like 92.4 at an angle of 76.87 degree. 92.4 at an angle of 76.87 degree. And if you expand it, take up real part and imaginary parts, you may get something like 21 plus J 90 ohms. will be coming like 21 plus j 90 ohms. 21 plus j 90 ohms. And you take up the imaginary part of that, imaginary part 90 ohms. I can say x is equals to 90 ohms. X equal to 90 ohms. That we substitute in the Pmax equation. That we will substitute in the P maximum equation to get the approximate value of P maximum. Okay. So let's say approximate P maximum P phase value by neglecting the series resistance as well as shunt admittances. 138 into 138 by 90. So it's kilo square means mega. Kilo square means it is mega. How much is that number? 138 into 138 by 90. How much is that? 211.6 megawatt. 211.6 megawatts. Kindly check that. 211.6 megawatts is the maximum power transfer capacity. Maximum power transfer capacity. Okay. So look at my question now. Look at my question. Listen, all of you. Listen kindly. Listen kindly. See, look, we have a transmission line outside, something like this. It's a transmission line. What we are looking outside, let us say, looking outside. This we have represented. This we have represented in a pi model. This we have represented in a pi model, like this. Okay. So is it exact model of line? Almost. Is it exact model of transmission line or not? Pi model, pi model. Kindly tell me your answer. Yes or no? Yes. It's an exact model, almost. So it's a exact, you can write approximately exact. See, this model we converted into a series reactance. This model we converted into a series reactance. Kindly observe. Series reactance. Is it approximate model now? Right. It's an approximate model. I think all of you getting this point. It's an approximate model. Anybody, please tell me, what is Pmax of this network we have? What's the Pmax of this network? 211.6 mega. 211.6 mega. So called Vs into VR by X. Can anybody tell me what is Pmax of this exact network or Pmax of this transmission line? Is it the P maximum of transmission line? Just listen my words, please. 211.6. Is it the maximum power transfer capacity of transmission line? Yes or no? It's no. It's a no. It's not the P maximum of the transmission line. It's a P maximum by making some assumptions. How is a P maximum of your transmission line? Exact transmission line. How is that? Means that value might be definitely low compared to 211.6. Might be low compared to 211.6. So I'll write here. Kindly follow it in the next slide. Exact value of P maximum will be exact value of maximum power transfer capacity will be. Look at the equation. Mod Vs mod Vr by mod B minus mod A by mod B mod Vr square cos of beta minus alpha. See, one thing. It's the exact P maximum. Approximate P maximum will be like Vs into Vr by X. Approximate P maximum is P maximum in bracket I'll say transmission line. I think that statement is okay. Transmission line P maximum is this one. And P maximum approximate is Vs into Vr by X. Vs into Vr by X. Then how is a transmission line P maximum compared to approximate value? That will be definitely less. Why it is so means this parameter B is greater than X. Just if you observe here, what is B? B may agree to 92.4. What is the X value? 90. So mod B is greater compared to X. That's one reason. And you are subtracting one term from this. You are subtracting one term from this one. So obviously Pmax of transmission line will be definitely less compared to the value of approximate P maximum. All of you getting this? Tell me please, from these two we are writing P maximum of transmission line wire will be less compared to P maximum approximate value. P maximum approximate value. Right. Good, good. So in recent years examinations of GATE, they have given this comparison. They have asked about this comparison. Asked about that comparison. Okay, I will give one more problem to you. Give one more problem in the similar way. As a small extension for the previous one. Extension for the previous one. I am giving one more problem. Sir, then what is the approximate value indicate? Jessica, that is just for to get an idea. Just to get an idea. Okay, P maximum of this line will be in and around 211. So it will be less than 211. So we should keep the loading with a good gap, with 211 to make that comment. Just for easiness and understanding, they will go with that. And a quick calculation, you can say better. Quick calculation. Same question. Same question I am repeating. Same question I have repeated. Just check this. Only one change I have made there. Just go through it. The ABCD constants of a nominal pi network, ABCD constants of a nominal pi network representing three-phase transmission line, are A equal to D, 0.95 at an angle 1.27 degree, B, same, C, same numbers. Find the steady state power limit if the sending end and receiving end voltages are maintained at 138 kV. Use the short line approximation. Use the short line approximation. Short transmission line approximation we have to use here. Short transmission line approximation we have to use. Yeah, please listen. Listen kindly what I am saying. What do you mean by short line approximation? What do you mean by short line approximation? Anybody? What do you mean by short line approximation? That is simply neglecting the effect of the shunt admittance. Neglecting the effect of the shunt admittance. That's it. That's it. Is it required to consider the series resistance into calculation? Is it required to take up the series resistance in the calculations? Yes or no? Series resistance. Yes, definitely we should take the series resistance value. We should not neglect it. Okay, fine. Only shunt admittance will be neglected. Shunt admittance will be neglected. Only shunt admittance will be neglected. So your line will be with the short line approximation, you will be getting something like this. Like this, we are going to get the line. And this is a series impedance Z, we can say. Series impedance Z. Forget about the problem. Forget about the problem what he is asking. Just concentrate in this one. Concentrate in this one. He is asking to find maximum power transfer capacity of this model. Maximum power transfer capacity of this model. So first you find out ABCD of this one. ABCD. A equals to 1, B equal to Z, C equal to 0, D equals to 1. Let's see. Okay. So I can say first A equals to 1, B value Z you can say, C value 0, D value 1. 1, Z, 0, 1 are the ABCD. Okay. Next thing. What is Pmax of this one? What is Pmax of this one? Don't remember a separate formula for short line. I don't advise you to remember a separate formula for the short line, you have to take up the same formula as it is of the ABCD. As it is of the ABCD. Okay. So what is the P maximum formula in the ABCD? P max equals to Vs into Vr by mod B cos beta minus delta is 1 for maximum condition minus mod A by mod B mod Vr square cos beta minus alpha. Cos of beta minus alpha. I think all of you getting this? All of you getting this? See, Vs and Vr values both are equal to 138 kV as it is given in the data. I will substitute 138 kV. I will substitute for this Vs and Vr. A parameter A, how much? All of you, please tell me. What's the parameter A? I need your response. Please tell me. What's the parameter A? 1. Parameter A is 1, 1, 1. Okay. I know parameter A already. C also I know. D also I know. B equal to Z. What is the Z? What is the Z for the line? In the problem, he said for nominal pi model, A, B, C, D are like this. Whatever the parameter B we have, that itself is a series impedance Z. That parameter B itself is a series impedance Z, we can say. So I can say from this, P is equal to Z, which is nothing but 92.4 at an angle of 76.87 degree ohms. Substitute all the numbers in this. P max. Vs into Vr. 138 into 138 by mod B minus mod A 1 mod B Vr square cos beta minus alpha. Beta minus alpha. Like this you can teach. Okay, it's kilo square R, so it will be megawatts. Come to be megawatts. How much is this number? How much is this number? Anybody? Yeah, please tell me. What is this number? 159.28 megawatts. 159.28 megawatts. This is a P maximum of the short line approximation. Short line approximation. Why we are not using given A? Abhijit, already they are using short line model. No, for short line model A equals to 1, right? The problem we asked to find out for short line model. Short line model parameter A equals to 1. That's it. So this is one of the untapped problem in the examination. Have to be very thorough about this problem. This is an expected problem in the gate. Expected problem in the gate examination. Okay, let's move. Let's move to some more problems in this power equations. Power equations. I'm taking up next problem. So you go through this. This one. Quickly. A 275 kV transmission line. 275 kV transmission line has the following line constants. Parameter A, 0.85 at an angle 5 degree. Parameter B, 200 at an angle 75 degrees. Only A and B they have given. 0.85 at an angle 5 degree. B, 200 at an angle 75 degrees. Look here. The transmission line is loaded by 150 megawatt UPF load. Line is loaded by 150 megawatt UPF load. The voltage profile at each end of the line maintained at 275 kV. Means sending an voltage 275, receiving an voltage is also 275 kV. By placing, look here, by placing a shunt compensation at the receiving end side. So at the receiving end side, he is keeping a shunt compensator. By keeping that, he is interested to maintain both receiving end and sending end voltages at 275 kV. The rating of that compensation equipment is how much in MVR? Rating of the compensation equipment is how many MVR? All of you getting this? Give me please. So I'm moving with the next slide. Just have a look here. So we have a 275 kV line here. Just observe how I am doing this. It is one of the classical model in the examination, GATE examination or any examination. It is one of the classical model. Like to maintain both ends voltages as equal, What is the rating of compensator to be kept at the receiving end side? What is the rating of the compensator to be kept at the receiving end side? Just observe the procedure. Try to learn this problem very clearly. Yeah. So these are ABCD parameters of the line. This side we might be having a source. Okay. And this side is saying we have a load. How much is the power demanded by the load? How much is the power demanded by load here? How much? 150 megawatt UPF. Load power demand is 150 megawatts. And power factor is 1. Unity power factor. Okay. See, if the power factor is 1 unity, how much amount of reactive power this load will draw? How much amount of reactive power this load is going to draw? How much? 0. As a power factor is unity, we can say this Q load value is equal to 0. This we are calculating it. Calculate. Q load value is equal to 0 because of unity power factor. Because of the unity power factor. Next. Listen please. See, sending end voltage. All of you stop writing and just check what I am asking. Sending end voltage, I am maintaining a 275 kV line to line. Sending end voltage, I am maintaining a 275 kV line to line. Receiving end voltage value may not be equals to 275. May not be equals to 275 kV. It may be more than 275 kV or less than 275 kV. Chances are there. That's the thing I am saying. All of you getting this diagram, what I have drawn? I need your response, please. I need your response. Yeah. See, sending end voltage 275, okay. Receiving end voltage may not be equals to 275. See, in order to maintain this receiving end voltage, also 275. He was interested to keep one shunt compensator at this particular bus. After keeping this compensator, this voltage was forced to 275 kilovolts. It is becoming 275 kV. 275 kV. Okay, next. Assume that. Or you tell me whether this compensator, is it a capacitor bank or reactor bank? Whether this compensator, is it a capacitor bank or reactor bank? We don't know that. First, let us assume that this compensator is injecting a reactive power of QC into the bus bar. This is injecting a reactive power of QC into the bus bar. See, after solving the problem at the end, if the QC comes to be positive, then I can say this as a capacitor bank. And if the QC comes to be negative, then this capacitor bank, so this is a reactor bank. And if this QC coming as 0, we no need to keep any compensator to make Vs equals to VR in magnitudes. Unity power factor, that is no losses, sending and voltage. What is that logic you are saying, Vijayarani? It's completely mistaken logic, what you are saying. Yeah. Look here, please. Okay. So our aim is to find out this QC value, how much amount of reactive power this compensator has to inject QC. Look here. See, in any examination anywhere, it is asking us to find out this reactive power or real power, whatever it is. Stand at this bus first. Stand at this bus. This bus. How many branches are connected to this bus? Anybody? How many branches are connected to that bus? 3 branches are connected. 3 branches. One is a line. Second, compensator. Third one, load. Line, compensator, load. For example, this line is injecting a reactive power into the bus like QR. Line is injecting a reactive power of QR into the bus. Load is taking a reactive power of Q load. Q load. Apply that reactive power balance here, just like KCL. Just like KCL application. 2 incoming, 1 outgoing. 2 incoming, 1 outgoing. What are the 2 incoming? QR plus QC. Outgoing Q load. So you can write now. QR plus QC is equal to Q load value. QR plus QC is equal to Q load value. Okay. And how much is Q load? Just now we said 0. Why? Because of unity power factor. Because of the unity power factor. So I can say Q load is equal to 0. From this, you can write compensator rating is nothing but negative of the QR. Compensator rating is equal to negative of the QR. Negative of the QR. Okay, now you take up the QR equation, what we have. Already we have derived in terms of ABCD, right? That equation you take for QR. After that, we will think what to do further. Yeah. Where reactive power injected by transmission line, into the bus, so called receiving and reactive power injection. Receiving and reactive power injection. QR is equals to, look at the formula. Mod VS, mod VR by mod V, sine of beta minus delta minus mod A by mod B, mod VR square, sine of beta minus alpha. Like this, mod VS, mod VR by mod B, sine of beta minus delta minus mod A by mod B, mod VR square, sine of beta minus alpha. Already I said, no, it's of unity power factor load. That's why this Q load is 0. Yeah. Else cos phi L is 1. What is sin phi L value? 0, right? Sin phi L is 0. Then this Q load formula is apparent power into sin phi L. Apparent power into sin phi L. Whatever may be the apparent power, as sin phi L is 0, Q load will be 0. Yeah, okay. Let's continue. Yeah, just look at this equation. Numbers you see. What are the values of VS and VR? What are the values of VS and VR? Both are equal to 275. Okay, let me substitute 275. What is mod B? Given in the data, 200. Mod B value 200 given in the data. That we substitute. Next thing. Sin beta. What is beta angle? Beta angle will be 75 degrees. Beta angle will be 75. Minus delta. What is delta actually? What is the delta? Anybody please tell me. What is the delta? Delta is an angular difference. Delta is an angular difference between sending end voltage to receiving end voltage. Delta is an angular difference between sending end voltage to receiving end voltage. For example, if your sending end voltage is at mod Vs at an angle delta, receiving end voltage is at mod Vr at an angle G. The delta is the angular difference between sending end and receiving end voltages. They have not given that value in the problem. They have not mentioned the value of delta in the problem. Is it the meaning to say it is 0? No, we should not say it as 0. We should not say that delta is 0. We don't know that value delta. It is required to calculate that in this problem. Okay, so most of the times in the examination, kindly listen. Most of the times in the examination, they may not give this delta value, so called the angular difference between the bus voltages. Okay, so that value we have to calculate to proceed further for the solution. So I can say this delta is an unknown angle. Unknown angle. Delta is an unknown angle which we have to calculate. Okay, let's take up this mod A. Mod A value, you know, it's 0.95, sorry, 0.85. Mod B, 200, VR square, 275 square, sine beta. Beta will be 75 degree, alpha, that is 0. Clear? So, this delta we have to calculate now. How to calculate the delta? How to calculate the delta? To calculate the delta, we have to use a real power equation. Because you see here, for example, in this diagram, real power injected by receiving end bus is PR. Real power injected by the transmission line is PR into the receiving end bus. You assume this compensator as lossless compensator. It's a lossless compensator. So it won't take any real power at all. So real power consumption will be 0. Compensator real power consumption is 0. But you know, we have some P load here existing. You know, some P load is existing. Now the thing is, real power injected by the transmission line into the bus, PR, real power injected by the line of the bus, PR, that is equals to P load because PC equals to 0. PR equals to P load, which is equals to how much? 150 megawatts. 150 megawatts. Let me write. Real power balance equation. Real power balance equation will give PR is equal to P load, which is 150 megawatts. PR is equals to P load, which is equals to 150 megawatts. Yeah, next. What is the equation for PR? PR equation. It will come as it is. But sine is replaced with cos. That's it. Again, in that equation, delta is unknown. In that equation also, delta is unknown. But I know the value of PR. That is 150. By doing that substitution, we will try to get that angle delta that we will substitute back into QR equation. Okay, so I'll write the PR equation. Mod VS, mod VR by mod V, cos of beta minus delta minus mod A by mod B, mod VR square, cos of beta minus alpha. So PR value, I will substitute 150 mega kilo square, mega, we'll keep it there. VSVR 275 kilo, 275 kilo square it is. Kilo square. What is mod B number? Mod B number is 200. Mod B number, it is 200. Cos of beta minus delta, that beta is 75 degree. Delta is unknown angle. Delta is unknown. What is mod A? Mod A value 0.85. Okay. By mod B, it is 200. Mod VR square means 275 square. Cos beta 75 degree, alpha 5 degrees. Alpha is given in parameter A angle 5 degrees. And you see kilo square, mega is common. That mega and this mega will be cancelled. Mega will be cancelled out. And you find out delta from this one. Find out the angle delta from this one. Find out that angle delta in degrees. You can't use approximate formula because he has given ABCD parameters, right? As he is giving ABCD parameters, you should not go for the approximation. If he has given only series reactance without any series resistance and shunt values, you can go with approximate formula Vs into VR by X. Unless otherwise, always it is better to go with the exact formula only in these calculations. 28.42 degrees is the angle. Angular difference between sending end voltage and receiving end voltage is 28.42 degrees. That you substitute back into QR equation. Therefore, QR is equals to Vs, VR by mod B. Mod B number, it is 200 sine beta minus delta minus mod A by mod B mod VR square sine of beta minus alpha. Sine of beta minus alpha. That's the reactive power QR. So you will be getting this number like minus 27.4. It's in megavolt amperes reactive. Kilo square means it is mega, kilo square mega. Reactive power means volt amperes react, where minus 27.4 MVAR minus 27.4 MVAR. That's the reactive power Q. But what we require to know, compensator rating, right? QC. QC is nothing but negative of QR. QC is equal to minus QR. That implies QC will come to be minus of minus 27.4, become like plus 27.4. Plus 27.4 MVR. Plus 27.4 MVR. See, not only this plus and minus symbols, kindly listen, Amrit Sagar, kindly listen to me. Not only this plus and minus symbols, we should know the direction of this Q also. Direction of the Q is also very, very important for us. Kindly observe. See, this is a direction of Q na, by compensator. This is a direction of Q, QC. Okay. See, actually, this is injecting a reactive power of QC. That QC is coming as positive number. Means obviously this compensator is injecting a reactive power of 27.4 MVR. 27.4 MVR. What is the nature of that compensator? It's a capacitor bank. We have to keep a capacitor bank at the bus bar. So compensator is a capacitor bank. Is a capacitor bank. Compensator is a capacitor bank. Right? So I think all of you getting this. We are keeping on load side only. What is that? Just change the position. Connected to the bus bar, that's the thing. Connected to the receiving end bus, that's the thing. Hey, I am saying you again and again. Don't think about the QC value positive or negative only. That's also one factor. QC positive and negative. Not only that, you should check the direction of the Q also. Direction of the Q also. Is it into the bus or out from the bus? That also we have to check. We are supplying plus 27.4 to maintain. Nah, it's not to maintain UPF. Already load power factor is unity. That's it. To maintain the voltage 275 kV, we are keeping the compensator. To maintain the voltage as 275 kV. 275 kV. Yeah, when it is capacitor, when it is inductor, that depends. That depends upon the value of voltage, exact value of voltage. Okay, listen to me. Very simple problem. Right? He is interested to maintain voltage at both sides as 275 kV. For that purpose, at the receiving end side, he is asking us to keep one compensator. That compensator rating we have to calculate. For that purpose, first we are applying reactive power balance at the receiving end bus. QR is injection, QC is injection. Sum of these two equals to Q load. Sum of these two equals to Q load. From that, we came to know QC equals to minus QR. QC equals to minus QR. Okay, next step. But if you look at the QR equation, delta will be unknown angle. To get the delta, we have to use the real power equation. After getting delta from real power equation, substitute that in the QC so that we can get the QC, and based on the QC plus or minus and direction of QC, we can decide what nature of compensator it is. Is it a capacitor bank or reactor bank? So anyhow, our answer will be C. Our answer will be C. Okay, done. Next. QC 27.4 is delivering. So it's capacitor compensation. Okay, yeah. Look here once. Look here, please. We have PR and QR equations now. PR and QR equations that I am taking up for time being. Just look these equations once. These equations I am copying. Set of equations. PR and QR. PR and QR. Yeah. Since so just observe the things what I am saying here. Observe the things. See this term mod A by mod B mod VR square cos of beta minus alpha, we'll assume as some constant A. Constant A. This we will be assuming as a constant B. This is constant A and this is constant B. That constant A you take to other side. Constant B also you take to other side. Then you will get here PR plus A. I'm removing else, but I'll write. PR plus A is equal to Vs into VR by mod B cos of beta minus delta. And QR plus B is coming like Vs into VR by mod B sin beta minus delta. Like this. PR plus A is Vs VR by mod B cos of beta minus delta. Second one, QR plus B is Vs into VR by mod B sin of beta minus delta. Like this, you are going to get. Next thing. Next slide I'm taking up. What will be this? PR plus A whole square plus QR plus B whole square. Tell me please. PR plus A whole square plus QR plus B whole square. What will happen? That will be this square plus this square. So I'll keep this one square plus the second term what we have here. Square. So in place of this cos, you will be getting sine. In place of cos, you will be getting sine. And obviously, this will be resulting into a term like Vs into VR by mod B whole square. Vs into VR by mod B whole square. So PR plus A whole square plus QR plus B whole square. PR plus A whole square plus QR plus B whole square is equal to Vs into VR by mod B whole square. Vs into VR by mod B whole square. So how this equation looks to be for you? How this equation looks to be for you? It will be a circle. This equation looks to be a circle. Okay, so it's a circle equation. Circle equation means if you take the complex power in a two-axis plane, x and y-axis plane, it looks to be a circle. If you plot If you plot the complex power, so-called PR and QR, it comes to be a circle. Okay, let me show in the next slide. Just as an indication, it's a PR axis. PR axis and this is a QR axis. Right? So the complex power, locus of the complex power will be a circle. Locus of complex power is a circle. Locus of the complex power is a circle. Okay. Can you please tell me what is the center of the circle now? What will be the center of the circle? Center. Minus A comma minus B. What are A and B? Just now I have shown here, Shahil, A and B. These are the numbers A and B. What is the center? Minus A minus B will be the center. Minus A minus B will be the center. And radius of the circle is Vs into VR by mod B. So I will write center minus A comma minus B, radius which is mod Vs into mod VR by mod B. Mod Vs into mod VR by mod B. Center is minus A minus B. Radius will be mod Vs into mod VR by mod B. Okay, done. So in the exam, there is a possibility. There is a possibility of asking you by giving some data. What will be the radius of the circle? Draw the complex power locus to be a circle for you. What will be the radius of the circle? That type of question we have a possibility of getting it in the examination. Okay, yeah. So next. So next we are going to discuss about the two-bus power system network. Two-bus power system network we are going to discuss. Mainly, we will try to see how to write the real and the reactive power equations in that, and how to decide real power flow direction, as well as how to decide the reactive power flow direction. With those aims, we are moving on to two-bus power system network. Yeah. So let's see. Here, two-bus power system network. Two-bus power system. It's also one of the very important one for the examination. Okay. Two-bus power system. Look this. See, this is a bus 1. We are calling here. It's a bus 1. And it's connected to bus 2. Bus. See, the complete analysis, whatever I am doing now from this point onwards, will be the approximate analysis. Complete analysis, whatever I am doing now will be the approximate study only. Approximate study means this is having only series reactance. Bus 1 voltage, mod V1 at an angle delta 1. Bus 2, mod V2 at an angle delta 2. Okay, bus 1 voltage is mod V1 at an angle delta 1. Bus 2 voltage is mod V2 at an angle delta 2. So let's say real power injection to this bus is P2. Reactive power injection is Q2. Real power injection I am showing as P2. Reactive power injection I am showing as Q2. P2, Q2. Yeah. I have to write these two equations. What is P2 equation and what is Q2 equation? That we have to write. Tell me please, what is the equation for P2? What will be the equation for P2? Anybody please tell me? Please tell me, what is P2? See, earlier we have written PR is equals to mod Vs mod VR by X into sine delta. Same thing we will write. Mod V1 mod V2. Mod V1 mod V2 by X reactance into sine of Angular difference between the bus voltages means you'll get this like delta 1 minus delta 2. Mod V1 mod V2 by X into sine of delta 1 minus delta 2. That's a real power injection P2. Real power injection P2. What is Q2? What is Q2? Tell me please, Q2. See, I'll tell the QR equation. QR equation we have written earlier like VR by X into mod Vs cos delta minus mod VR. Na? QR equation is mod VR by X into mod Vs cos delta minus mod VR. Okay, that mod VR we have to replace with mod V2 X. Okay, mod Vs we should replace with mod V1. Delta we have to replace with delta 1 minus delta. Delta 1 minus delta 2. Mod VR is again mod V2. Mod VR will be again mod V2. Let's replace the things. Replace the things. So again, mod V2 by X here into mod V1 cosine delta 1 minus delta 2 minus mod VR is like this. You can get the Q2 equation. Reactive power Q2 equation. P2 and Q. Next thing. Now tell me please, who will decide? Who will decide whether the P2 is positive or negative? Whether the P2 is positive or negative, who is going to decide it? Tell me please, is it going to be decided by V1, V2 by X? Whether the P2 positive or negative, will it be decided by V1, V2 by X? Yes or no? No, it's not going to decide. Who is going to decide here? It will be decided by delta 1 minus delta 2 L. If the delta 1 minus delta 2 is a positive number, then you can say P2 is positive. P2 is positive in the sense, P2 is positive in the sense, bus 2 is taking real power. P2 is positive means bus 2 is taking real power. Who is supplying that now? Bus 1. So we have a real power flowing from bus 1 to bus 2. Bus 1 to bus 2, if the delta 1 minus delta 2 is positive. Delta 1 minus delta 2 is positive. Okay, so I'll write in the next slide. Real power flow direction is our heading, of course. P flow direction is our heading. P flow direction. See this. First, if delta 1 minus delta 2 greater than 0 or delta 1 is greater than delta 2, then it is observed that P2 is positive. P2 is positive in the sense, P2 is positive in the sense, real power will flow from bus 1 to bus 2. That implies P, real power flows from bus number 1 to bus number 2. Real power will be flowing from the bus number 1 to bus number 2. Bus number 1 to bus. Next thing. If the delta 1 minus delta 2 less than 0 means it is negative. Negative means delta 1 is less compared to delta 2. Let's delta 1 less compared to delta 2. It is negative. Negative means obviously P2 is negative. Then I can say that P2 is negative value. Whenever the P2 is negative, look here please. Look here please. P2 is negative. P2 is negative means bus 2 is absorbing negative real power. If bus 2 absorbing negative real power, is it absorbing the real power or delivering real power? Is it absorbing real power or delivering real power? Delivering real power. So bus 2 delivering real power means it is flowing through bus 1. So real power will be flowing from bus 2 to bus 1. Real power will be flowing from bus 2 to bus 1, we can say. That implies real power flows from bus number 2 to bus number 1. Real power will be flowing from the bus number 2 to bus number 1. Bus number 2 to bus number 1. Tell me please, who is going to decide the real power flow direction here? Is it from bus 1 to bus 2 or bus 2 to bus 1? Who is deciding that? who is deciding that the real power flow here? Bus 1 to bus 2 or bus 2 to bus 1? Yeah. Yeah, that will be decided by angular difference between the bus voltages. Angular difference between the bus voltages. So who is going to decide means, for example, in the case 1, delta 1 more than delta 2. Delta 1 more than delta 2. Power is flowing from bus 1 to bus 2. Second case, delta 2 more than delta 1. Power is flowing from bus 2 to bus 1. So the real power will flow from higher voltage angle bus, to the lower voltage angle bus. Higher voltage angle bus to lower voltage angle bus. This real power will be carried out. So I can say P flows from generally right here. That statement clearly. Generally, P flows from higher voltage angle bus to lower voltage angle bus in the sense, if you show these two voltages in the phasor diagram, whichever the voltage phasor is in leading, from that leading voltage phasor to lagging voltage phasor, this real power will be carried out. So P flows from leading voltage phasor to a leading voltage bus to lagging voltage bus. Lagging voltage bus. Leading voltage bus to lag. Okay. So I think all of you have understood this statement, what I said? Statement. And this statement is having some condition that the system is lossless. System is lossless means does not have any resistance. Else we can say the system is having high X by R ratio. Okay. So provided that the system is lossless or having high expire issue, high expire ratio, having high expire issue. Okay, so have a break for 5 minutes. After break, we will be continuing with the reactive power flow direction. So after break, we will be continuing with reactive power flow direction. I have resumed audio video on screen. Yeah. So kindly look at this. So this is about the real power flow direction. I am saying particularly for a lossless system. Lossless system, from leading voltage bus to lagging voltage bus, we will be having the real power flow. Real power flow. Okay, next. So let's think about the reactive power flow direction now. Let's think about the reactive power flow direction. Tell me please, this delta 1 minus delta 2, what we have inside, delta 1 minus delta 2. It's a positive angle or it may be a negative angle. For example, positive or negative, whatever it is. Because we have a cosine here, na? Cosine of positive, cosine of negative, that will be same value. Means same positive value only I am saying. So this delta 1 minus delta 2, whether it is positive or negative, it is not going to decide. It's not going to decide whether this Q2 is positive or negative. Then who will decide means, this first term, V1 cos of delta 1 minus delta 2, compare it with V2. V1 cos of delta 1 minus delta 2, compare it with V2. This comparison will decide whether this Q2 value positive or negative. Positive or negative. Yeah. Listen, please. Listen. See, first I can say if that mod V2 value greater than V1 cos of delta 1 minus delta 2, then this Q2 will be negative number. Q2 will be negative number. If that is negative, bus 2 is taking negative reactive power. Bus 2 is taking negative reactive power means it is not absorbing reactive power, it is delivering reactive power, we can say. Okay. Similarly, V2 is less. V2 is less compared to V1 cos of delta 1 minus delta 2. In that case, Q2 will be positive. So bus 2 is absorbing the reactive power, we can say. Okay. So who is going to decide the reactive power flow direction now? Comparison between this mod V1 and mod V2 values. Strictly speaking, mod V1 cosine of angle and mod V2. This comparison is going to decide the Q2 number. Is it positive or negative? Yeah. So let's say Q flow direction here. Flow direction. Reactive power flow direction. First statement I am saying, if mod V2 number less compared to V1 of V1 into cosine delta 1 minus delta 2. Mod V2 value less compared to this one. Then Q2 is positive. Then Q2 is positive. See, whenever the Q2 is positive, I can say that implies bus 2 absorbs reactive power. That's it. Okay. Other statement opposite. Mod V2 greater compared to V1 cos delta 1 minus delta 2. Mod V2 is greater compared to V1 cos of delta 1 minus delta 2. Then Q2 will be negative. So Q2 is negative in the sense this bus is absorbing negative reactive power, means it's going to deliver the reactive power. That implies bus 2 delivers reactive power. Bus 2 is going to deliver the reactive power. Now you please tell me, who is going to decide reactive power flow here? Magnitudes of the voltages comparison. If the voltage magnitude is low, it is absorbing the reactive power. If the voltage magnitude is high, it is delivering the reactive power. So I can say here, generally reactive power will flow from higher magnitude voltage terminal to lower magnitude voltage terminal. Higher magnitude magnitude voltage terminal to voltage terminal to lower voltage magnitude terminal. Lower magnitude voltage terminal. Lower magnitude voltage terminal. Higher magnitude voltage terminal to lower voltage magnitude terminal will be having the reactive power flow direction. Reactive power. I will add one more small comment here. Provided that both voltages are taken on same reference. Provided that both voltages are taken on same reference. Okay. I'll show you how that meaning of same reference and all for time being. Just look here. We have two buses with bus 1 voltage mod V1 at an angle delta 1. Bus 2 voltage mod V2 at an angle delta 2. Mod V1 at an angle delta 1. Mod V2 at an angle delta 2. Let us show that. Let us show the two voltages in a phasor diagram. Just observe here. This is mod V2 at an angle delta 2. V2 phasor, and that is at an angle of how much? Delta 2. Delta 2 means I am showing some simple reference line here. Check it out. Check this reference line. Yeah. And this is at an angle of delta 2. At an angle of delta. It's a reference, some reference. Okay, look here. I want to show V1, mod V1 at an angle delta 1. I want to show mod V1 at an angle of delta 1. Let us assume delta 1 is greater compared to delta 2. Let's assume that delta 1 is greater compared to delta 2. Then how is a V1 phasor? It will be in leading with respect to V2. Na? V1 phasor will be in leading with respect to V2, something like this. Let's say like this. Okay. So this is the V1 phasor. How much is the angle made by this V1 phasor? Delta 1 is a angle. Delta 1 is the angle made. Okay. Now could you please tell me what is this angular difference between V1 and V2? What will be that angular difference between V1 and V2? Tell me please. Delta 1 minus delta 2 is that angular difference. Delta 1 minus delta 2 is that angular difference between V1 and the V2 phasors. Okay, next. Listen all of you. Don't confuse. Kindly don't confuse. I'm asking one very simple question to you. On which bus we are standing and discussing about real and reactive powers? On which bus? Which bus we are standing and discussing about the real and reactive powers here? Anybody? Please tell me. On which bus we are standing and discussing about real and reactive powers? Bus 2. That's it. Look now. So bus 2 voltage I have taken as a reference now. Bus 2 voltage I have taken as a reference because bus 2 is the bus on which we are standing. Now refer the bus 1 voltage onto bus 2. Refer the bus 1 voltage onto bus 2. What do you get this one? What do you get this? Bus 1 voltage we are referring onto bus 2. It will be V1 cos of delta 1 minus delta 2. That will be coming like V1 cos of delta 1 minus delta 2. All of you getting this one? V1 cos of delta 1 minus delta 2. Are we comparing this V1 cos of delta 1 minus delta 2 with V2? Are we comparing these two to check whether the bus 2 is delivering real power or delivering reactive power or absorbing reactive power? Yes or no? Only these two values we are comparing. Yes or no? Yes. So that's the meaning of both voltages are taken on the same reference. That's the meaning of both voltages are taken on the same reference. See, both voltages are taken on the same reference means it's not a common reference. It's not a common reference here. Whichever the bus you are standing, that bus voltage itself we should take as a reference. We should take as reference, and we should refer the other bus voltage onto that, and then we have to compare these two voltages to decide whether that bus is delivering the reactive power or absorbing the reactive power. I don't know whether you have understood this or not. All of you clear about this? All of you clear? Yeah, fine. Good. Next thing. Listen, please. Listen, please. For example, to decide reactive power at bus 1 means bus 1 whether it is going to deliver the reactive power or absorb the reactive power. Bus 1. What you have to do? We have to take bus 1 voltage as a reference. We have to take the bus 1 voltage as a reference, and you should refer bus 2 voltage onto that. All of you getting my point? Bus 1 voltage you take as a reference, and then bus 2 voltage referred onto that. That comparison will tell whether the bus 1 is delivering Q or absorbing Q. What is V2 referred onto V1? What is V2 value referred onto V1? Yeah, tell me please. What is V2 referred onto V1? V2 cosine of the angle gap. V2 cosine of the angle gap. Okay, so that comparison with V1 will decide whether the bus 1 is delivering or absorbing the reactive power. Okay, next thing. Let's continue. So I'm taking up one small example to give more clarity. Whatever the things you have in your mind, just leave it. Just take it out first. Just listen concentratedly whatever I am saying. Okay. Look here. Example I'm taking up. So I have a two-bus system like this. Bus 1 voltage is like 1 at an angle minus 20 degrees. Bus 2 voltage is like 1 at an angle minus 10 degrees in per unit. It's a reactance only. There is no resistance, only it is reactance. Bus 1, bus 2. Bus 1 and it is bus 2. Look please. Bus 1 at an angle minus 20. Bus 2, 1 at an angle minus 10 degrees. Observe here. Magnitude of bus 1 voltage 1 per unit. Delta 1 minus 20 degrees. Mod V2 1 per unit. Delta 2 minus 10 degrees. Delta 2 will be minus 10 degrees. Now tell me, from which bus to which bus real power will be flowing? From which bus to which bus reactive power will be flowing? That's the question. Real power direction. Which bus to which bus it will be flowing real power? Bus 1 to bus 2 or bus 2 to bus 1? See, we have to compare delta 1 with delta 2. Delta 1 minus 20, delta 2 minus 10. Which angle looks to be greater? Delta 2 looks to be greater compared to delta 1. As delta 2 is more compared to delta 1. So real power will be flowing from bus 2 to bus 1. So I can say as delta 2 is greater than delta 1, the real power will flow from bus 2 to bus 1. Bus number 2 to bus number 1. Okay. Real power will be flowing from bus number 2 to bus number 1. Next thing. Reactive power flow. All of you please tell me reactive power. Which bus to which bus reactive power will be flowing? Is it from bus 1 to bus 2 or bus 2 to bus 1? Bus 1 to bus 2 or bus 2 to bus 1? Let us take up Let us take a bus 1 calculation. Bus 1. All of you stop writing. All of you stop writing and just listen whatever I am saying. Whatever I am saying. Bus 1, we are standing. We are standing at bus 1. Who is your reference? Bus 1, we are standing. Who is your reference? Stop writing and just listen. Bus 1 is a reference. Nah? Bus 1, we are standing means bus 1 itself is our reference. So, mod V1, you should take directly 1 per unit, whatever it is given. Mod V1, you should take directly. Next, bus 2 voltage referred on to bus 1. Bus 2 voltage referred on to bus 1. V2 cos delta 1 minus delta 1. V2 cos delta 1 minus delta 2. So it is 1 into cosine of this angle gap. Angle gap will be minus 20 minus 10. It will be like 10 degree, I think. So. Minus 20 minus of minus 10. So it will be 10 degree. Cos 10. How much is that number? How much is that number? 1 into cos 10 degree. Anybody? 0.98 something. 0.98. Tell me now. Tell me now. How is a bus 1 voltage magnitude compared to the other number? Greater. Bus 1 voltage magnitude is greater compared to the other number. Means whether the bus 1 is absorbing the reactive power or delivering the reactive power. Bus 1 absorbing reactive power or delivering reactive power? Delivering. Because bus 1 voltage magnitude looks to be greater. I think all of you getting my words, what I am saying here. Yeah. So I can say as mod V1 value greater compared to V2 cos delta 1 minus delta 2, bus 1 will deliver the reactive power. Will deliver reactive power. Bus 1 will be delivering the reactive power. Okay, done. Next thing. Bus 2. Bus 2. Yeah. If you are standing at bus 2, who is your reference now? Bus 2, who is your reference? V2. V2 voltage itself is your reference. So V2 we should take as it is. V2 we should take as it is without any change. V2. Okay, now other bus is V1. Na? Other bus voltage is V1. V1 referred on to V2. V1 referred on to V2 means it is V1 cosine delta 1 minus delta 2. So it is 1 into cosine delta 1 minus delta 2 means what? Minus 20 plus 10 degree. So it will be cos 10 degree again. So you'll get this number 0.98. That number will come to be 0.98. Here, 0.98. Tell me now, whether the bus 2 is delivering to or absorbing to now? Whether that bus 2 is delivering the reactive power or absorbing the reactive power? Anybody, please tell me. Bus 2 will be delivering again. Why it is absorbing, Ashish? It will be delivering again. Why? In the sense, V2 is greater compared to this number. Na? V2 greater compared to V1 cos of this angle gap. So that implies bus 2 will deliver the reactive power. Will deliver the reactive power. There is no mistake in the statement as well as there is no controversy. There is no mistake as well as there is no controversy. Okay. So the understanding what you have to make here. The understanding what you have to make here is bus 1 voltage magnitude and bus 2 voltage magnitudes both are equal magnitudes. Magnitudes both are equal. In this condition, bus 1 is delivering the reactive power. Bus 2 is also delivering the reactive power in this case. Right? Mod V1 is 1 per unit. Mod V2 is also 1 per unit. In this situation, bus 1 is delivering the reactive power into the line. Bus 2 is also delivering the reactive power into the line. So whatever the reactive powers injected by both buses into the transmission line, that will be absorbed by the transmission line itself. Okay, so If mod V1 and mod V2 values are equal, then both buses will deliver reactive power into the transmission line, and it will be absorbed by transmission line itself. It will be absorbed by transmission line itself. It will be absorbed by the transmission line itself. All of you understood this meaning? All of you understood this meaning? I will explain you again. Just listen. Don't confuse. Saying about real power direction, real power direction is very easy. Saying about real power direction is very easy in the sense, if one bus is delivering real power, means other bus will be absorbing it. Definitely. So if one bus is absorbing real power, then obviously other bus is supplying it. But reactive power is not in that manner. We can't decide exactly from which bus to which bus this reactive power is flowing. Can't decide exactly from which bus to which bus this reactive power is flowing. For example, at bus 1 you are doing bus 1. What you are saying here, bus 1 will deliver the reactive power. According to the calculations at bus 1, what we are confirming is bus 1 is delivering reactive power. That's it. Bus 1 delivers the Q. That's it. I don't know about bus 2. Is it absorbing the Q or delivering the Q? I don't know about it. Okay. Similarly, at bus 2, we have written a statement. Bus 2 will deliver the Q. That's it. I don't know about bus 1. Bus 2 is delivering the reactive power. I don't know about bus 1. Is it absorbing or is it delivering? Following all of you. So I think all of you getting this meaning of reactive power flow direction. Yes, Imtiaz. Yes, Imtiaz. This is not a midpoint compensation. This Q goes into inductance of line. Okay. Yes, correct. Yeah. So I'm moving to next slide to discuss some more thing. I'm moving to next slide. All of you stop writing. Just listen here what I am saying you. Stop writing completely. Put your pen aside. Just listen. It's a bus 1. Bus 2. Bus 1, mod V1 at an angle delta 1. Bus 2, mod V2 at an angle delta 1. Reactance is X. Okay, next thing. Sir, where we found reactive power? What's your doubt, Mamata? You ask me in doubt session, please. What's your doubt? Listen here first. Listen. Some simple questions I will ask you. Just answer them. That's it. This is some reactive power Q2. That is some reactive power Q2. Look, which bus you are standing? Bus 1 or bus 2? Tell me please. Bus 2. Clear. So I should write V2 by X. Bus 2 I am standing. I have written V2 by X. Direction of Q. Direction of reactive power. Which bus to which bus? Direction of reactive power from which bus to which bus? Tell me please. Direction. 1 to 2. I have shown in the diagram. I'm not saying that reactive power is flowing in this direction as positive number. I have shown the direction. That's it. 1 to 2. I have given the direction in the figure. 1 to 2. So I should write here V1 minus V2. I should write V1 minus V2. Bus 1 to bus 2. V1 minus V2. V1 minus V2. Asking you again, who is your reference? Who is your reference? V2. V2 is your reference, na? V2 is our reference. V2 is our reference means V2 you keep as it is. V2 you keep as it is. V1 you replace with V1 into cosine of angle gap. V1 you replace with V1 cosine of angle gap. And V2 you keep as it is. This is the Q2 equation outright. This is a way of writing the Q2 equation without by-hearting the equation. Without by-hearting the equation. Yeah. Is it okay? Is it okay for you? Why bus 2 reference means we are standing at bus 2 only, na? We are doing our calculation at bus 2, so bus 2 is our reference, obviously. I'll write. Listen. This is Q1. Tell me. Q1. Which bus you are standing? Which bus you are standing? Bus 1. So what I have to write first? V1 by X. Bus 1 I am standing, so I have to write V1 by X. Direction of reactive power. Which bus to which bus I am showing here? Which bus to which bus I am showing the direction of reactive power? 1 to 2. 1 to 2. 1 to 2, not 2 to 1. Just check the direction. Check the direction and tell me. 1 to 2 only. 1 to 2. Okay. 1 to 2. 1 to 2 means what I should say? V1 minus V2. 1 to 2 means 1 minus 2. V1 minus V2. Who is your reference? Who is your reference? V1 is our reference. V1 is our reference means V1 you keep as it is. V1 you keep as it is. V2 replaced with what? V2 replaced with V2 cosine of angle. V2 replaced with V2 cosine of the angle. This is the Q1. That's the Q1. Getting? All of you getting it? Next thing. See this. Here's some QX, or whatever it is, QX. Look again. QX. Which bus we are standing for QX? Which bus we are standing for QX? Bus? Yeah, 1 minute please. In this method, we don't need to consider which one is delivering and which one is absorbing Q. Yeah, why you are bothering about that, Shiva? Why you are bothering about that? Listen, bus 1. So bus 2. Bus 2 means what you should write? V2 by X. Direction from which bus to which bus? 2 to 1. 2 to 1 means what you should say? V2 minus V1. V2 minus V1. Who is your reference? V2. We keep as it is V2. V1 replaced with what? V1 cosine of angle gap. V1 cosine of angle. I think all of you have understood this way of writing reactive power. All of you understood this way of writing reactive power? Yeah. So real power, it is very easy to write. Real power, simply magnitudes of the voltages product by reactance into sine of the angle difference. Sine of the angle difference in the direction of real power you have taken. For example, if you have taken real power from bus 1 to bus 2, you get delta 1 minus delta 2. If you have taken from bus 2 to bus 1, you will get delta 2 minus delta 1. That's only the change you can expect in the real power. But reactive power is very sensitive equation. Very difficult to write, but you have to remember this procedure of writing the reactive power equation all the time. What if it is a 3-bus system? I'll tell you. Pratyusha. I'm showing in the next slide. Look here. For example, this is bus 1, V1 at an angle delta 1, bus 2, V2 at an angle delta 2, bus 3, V3 at an angle delta. V3 at an angle delta. Okay, at which location you want? Please tell me. These are all approximate equations only by considering x. Considering x. All of you, please tell me which bus you want me to take. Which bus you want me to take? Yeah. Bus 2? Okay, fine. Bus 2 I'll take. Bus 2. Listen. Bus 2. I will have two paths in bus 2. Two paths at bus 2. This is one path. Q2, 3, I will say. This is the other path. I'll call this is Q21. Could you please tell me what is Q23 equation? Q23 equation. Simple, very simple. Just listen my words. Listen my words. Which bus we are standing? Which bus we are standing? Bus 2. Bus 2. Bus 2 means mod V2 by what reactance I should take? This reactance. X23 I should take, na? Because that's the direction. That's the flow. Okay, X23 reactance. X23. Direction from which bus to which bus? 2 to 3. 2 to 3 is a direction. So we have to call V2 minus 2 to 3 is a direction. So we should call V2 minus V3. V2 minus V3. Now the thing is, who is your reference? V2 is our reference. So you keep V2 as it is. V3 replaced with V3 into cosine of angle between these two. Cosine of angle between bus 2 and bus 3 voltages. Bus 2 and bus 3 voltages. Like this, you can get the Q23 equation. All of you getting? Yeah. All of you getting it? Q23? Pratyusha, are you clear? Okay. Q21 equation. Q21 equation. Which bus we are standing? Bus 2. So you get V2 by X12. V2 by X12 because Q is given into the line X1. Into the line X1. V2 by X12. Direction. Bus 2 to bus 1. So you write V2 minus V1. V2 is a reference. You keep as it is. V1 replaced with V1 cosine of angle gap. V1 cosine of angle gap. Like this, you can get the Q21. Is it possible to calculate Q13 directly? Q13. No, there is no meaning of getting Q13 here. There is no meaning of getting Q13. Okay. See, always, Vikrant, we are going to find the reactive power direction at a bus. At a bus, that's it. Not from one bus to other bus. Not from one bus to other bus. Okay, fine. So let's take some simple problems on this. Simple problems on this two bus system. It's very, very important for examination, as I said. Let's take a problem here. Already we discussed about this problem in previous case. Just go through it now. Just go through it. It's a previous GATE examination question. Previous GATE exam question. Just go through it. For the system shown below, SD1, SD2, these are complex power demands at bus 1 and bus 2 respectively. Bus 1 complex power demand 1 per unit. Bus 2 complex power demand also 1 per unit. If mod V2 is equal to 1 per unit, mod V2 value 1 per unit is set. The VR rating of the capacitor QG2 connected at the bus 2 is similar problem, right? Earlier we have done capacitor bank rating calculation. Here also same, but here The line is given with only reactance. Z equals to J 0.5 per unit. Means we have only series reactance. So we can do this problem with the approximate equations. We can do this problem with the approximate equations. Okay. Yeah. So let's say in the next slide in the solution. Let's take that single line diagram first. Let's take that single line diagram. Yeah. See this one, single line diagram. Observe now. See, we have to find out this QG2. Already he said V2 magnitude is 1 per unit. 1 per unit. All of you, please tell me. Do you have any angle difference between bus 1 and bus 2 voltages? Do you get any angular difference between bus 1 and bus 2 voltages? Yes or no? Yes, definitely. Even though they didn't show that in the problem, still there will be a angular difference. So I will be taking up this bus 2 voltage as mod V2 at an angle delta. Mod V2 at an angle delta. That's the bus 2 voltage. Already we said bus 1 voltage is 1 at an angle 0. 1 at an angle 0. Clear? Next thing. SD1 1 per unit. What is this SD? Is it apparent power or complex power? SD. Is it apparent power or complex power? Complex power. It is complex power. Complex power is 1 means we have to write it as 1 plus J0. Complex power is 1 means we have to write it as 1 plus J0 means 1 real power, 0 reactive. 1 real power, 0 reactive power. So I'll write this like 1 plus J0 per unit. Similarly, SD2 complex power is 1 means you can write it as 1 plus J0. 1 plus J0. Okay. Now, next thing. Kindly observe. See, I have to find QG2. Na? So this is amount of reactive power injected by the capacitor bank into the bus. Amount of reactive power injected by the capacitor bank into the bus. See, let us see. Line. This line is injecting a reactive power of Q2, let us say. That line is injecting a reactive power of Q2 into the bus. SD2 complex power 1 plus J0 means this is demanding a reactive power of 0. Demanding a reactive power of 0. Reactive power is 0. Apply Q balance. Q2 injection. QG2 injection. So Q2 plus QG2 equal to QD2. Q2 plus QG2 equal to QD2. From that, you should get the QG2 value as we have done earlier. Let us show in the next slide. So here, Q balance at bus 2. Q2 injection plus QG2 injection equals to QD2 number. QD2 number is 0. So QG2 will come to be negative of Q2. QG2 will come to be negative of Q2. Negative of Q2. Okay. What is Q2 formula? What is that Q2 formula? Where Q2. Tell me please, Q2. Which bus you are standing? Bus 2. So we should write mod V2 by X. X is 0.5. Mod V2 by X. Direction from which bus to which bus? Bus 1 to bus 2. So it is mod V1 minus mod V2. Mod V1 minus mod V2. Mod V1 minus mod V2. Who is your reference? Who is your reference now? V2 is a reference. So V1 replaced with V1 of cosine of angle. V1 into cos delta. V1 into cos delta minus V2. Like this you can see. Yeah. So let's keep the numbers. V2 1, X value 0.5. Okay. V1 1 and V2 1. Delta is unknown. Delta angle is unknown. How to get the delta angle now? How to get the delta angle? Kindly look here. How to get the delta angle? To get the delta angle, we should follow the real power balance. Same as previous. We should follow the real power balance. Let us assume this line is injecting a real power of P2. Line is injecting a real power of P2. And this Pg2 0. It don't have any real power consumption, so Pg2 is 0. But you have a demand PD2, how much? 1 per unit. PD2 is equals to 1 per unit. 1 per unit. So I can say real power balance. Real power balance at plus 2. Real power balance at that plus 2. What it is now? P2 equals to PD2. P2 equal to PD2. How much is the PD2 value? That is 1. 1. What is P2 equation? What is P2 equation? Mod V1 mod V2 by X. Look my words please. Mod V1 mod V2 by X into sine of angle between these two means sine of 0 minus delta. Sine 0 minus delta. That is equals to 1. V1, V2 values are 1. Okay. X value 0.5. Sine of minus delta is equal to 1. So sine of minus delta value 0.5. 0.5. And if you calculate delta from this one, you may get minus 30 degree. Delta, you can get it as minus 30 degrees. Minus 30 degrees. Pg2 is 0 only, na? It's a capacitor bank which don't consume any real power. It won't consume any real power. It's a reactive element. So now the delta equals to minus 30, you substitute in the Q2 equation now. So therefore, Q2 will come to be mod V2 by X into mod V1 cos delta minus 1, like this. So this value you may get like minus 0.268 per unit. At Q2 value, we are going to get like minus 0.268 per unit. But what we need now? QG2, right? What is QG2? Negative of Q2 as QG2 is equal to negative of Q2. So minus Q2 means it will be minus of minus 0.268. So it will come to be plus 0.268 per unit. Come like plus 0.268 per unit. Already I discussed Q2 equation many times. Many times I said you how to write that Q2 equation. Yeah. So this is a rating of the capacitor bank plus 0.268. Check the options. Option B is a correct one to be chosen. Correct answer is B. Okay. Next. Next thing. Next problem you can see. So this is also one of the previous GATE examination question. It's also previous GATE examination. Just go through it. This one. So these are the options I have shown. Okay. Say, consider the two-bus system, two-bus power system network with given loads as shown in the figure. Given loads as shown in the figure. All the values shown in the figure are in per unit form. All the values shown in the figure are in per unit form. The reactive power supplied by the generator G1. Reactive power supplied by the generator G1 and G2 are QG1 and QG2 respectively. We have shown those two terms in the figure. QG1, QG2 respectively. The per unit values of QG1 and QG2, and line reactive power loss respectively are as given 4 options here. 4 options they have given. This balancing strategy always works. What is the balancing strategy I have used? What is the balancing strategy? Didn't get you. Yeah, listen, please. Say, let's copy this diagram what they have given. Two-bus system. Two-bus system. Yeah. Look here, please. Look here. See, first we have to find this QG2. Let's consider QG1. Let's concentrate on QG1 first. QG1. Very simple thing. Very simple thing. For that bus 1, how many branches are connected? For that bus 1, why should there be an angle difference between the two buses? Because of power flow. Because of power flow. Yeah, listen please, listen. QG1. How many branches are connected? 3 branches. One is generator branch, next one line branch, next one is a load branch. This injection is QG1. This reactive power you assume as Q1. Line reactive power is the bus 1, bus 2. Q1. This reactive power you take as QD1. This reactive power you take it as QD1. Now you can write simply QG1 equals to Q1 plus QD1. QG1 reactive power is nothing but QD1 plus Q1. What is QD1 number? 5. QD1 number is 5 per unit. What is Q1 number? That we don't know. Q1 number we don't know. That we have to get. Write the equation for Q1. Check how to get it. Okay? Yeah, that's sure. The next here itself Q1 equation. Q1. On which bus we are standing? Bus 1. So you should write V1 by X. Not V1 by X. See, this Q1 we are calculating only in the transmission line. Only in the transmission line, not the load and generator. Whatever the equation I am writing, that is the amount of reactive power in the line, in the transmission line. Okay, V1 by X. Direction. Direction from which bus to which bus? 1 to 2. 1 to 2 is our direction, means you should write V1 minus V2. Who is your reference? V1 is our reference. So V2 we should replace with cosine of angle. V2 we have to replace with cosine of the angle. Clear? QD means it is a reactive power demanded by load. Reactive power demanded by load. It is PD1 plus J times of QD1 in the general notation. In the general notations. Okay. Next thing. What is V1? 1. Okay. X 0.1. V1 X. V2 1. Delta is how much? We don't know. Delta we don't know. How to get the delta? That delta we have to get by using real power balance. By using real power balance, we have to get the delta. Okay, look here, please. Look here. This is a PG1 injection 20. PG1 injection 20. This is P1 outgoing, we don't know. P1 outgoing, we don't know. It is PD1 drawn by the load 15. 15 is a power drawn by the load. So I can write by real power balance at bus 1. Real power balance at bus 1. Balance at the bus 1. So I can write PG1 injection is equal to Pg1 injection equals to P1 plus PD1. P1 plus PD1. What is Pg1 value? 20. P1, I don't know. PD1 how much? 15. 15. So the value of P1 is 5 per unit. Value of P1 is 5 per unit. Actually, in the examination, we should not write all these steps also. Just by looking at this itself. Okay, it is injecting 20 per unit, and in that 15 per unit is drawn by the load. Remaining 5 per unit will go into the line. That's it. Remaining 5 per unit will go into the line. What is the equation? Mod V1 mod V2 by X into sine of delta minus 0. Sine of delta minus 0. So as we know, P1 equation here, as we know, P1 equation is mod V1 mod V2 by X into sine of delta minus 0. So that is sine delta. So it is 5. So V1 into V2, 1 into 1. X value. How much is X value? 0.2. So it is sine delta. Okay. So what you get sine delta from this now? 0.5 per unit. And delta will come to be 30 degrees. Delta angle will come to be 30 degrees. Okay. Now, by using the delta 30 degrees, we can get the value of Q1. So therefore, Q1 is equals to V1 by X. V1 by X means 1 by 0.1. 1 by 0.1 into V1, 1 minus 1 into cos delta. Delta is 30. Get this number, please. Get that number, please. How much is that number? Anybody? What is this number? 1.34 per unit. 1.34 per unit. Now, therefore, generator 1 reactive power supply, QG1 equals to 5 plus this 1.34. So 5 plus 1.34, it will come to be 6.34 per unit. 6.34 per unit is that reactive power. QG1 value. Check the options. Which any option is matching with 6.34. Yeah, two options are matching. And we have to find out reactive power generated by second generator. Reactive power generated by second generator we have to get. Look here. This is QG2. And QD2 how much? 10. And this is Q2 that we don't know. We have to get it. Q2 we don't know. We have to get that number. Then we have to add this Q2 and QD2 to get the value of QG2. Directions you can take as your wish, no issue. Directions you can take as your wish. But QG2 will be in this direction. So I can say QG2 will be equals to Q2 plus QD2, whereas this QD2 number is 10 per unit. And Q2 equation, if you write, what's the equation for Q2 you can write now? Q2. Mod V2 by X. Mod V2 by X into direction of the reactive power. Direction. Shown from which bus to which bus? Bus 2 to bus 1. So we get mod V2 minus mod V1. Mod V2 minus mod V1. Mod V2 is your reference. We should keep as it is. V1 replaced with V1 cos delta. So what is the V2 number? 1. X value 0.1. So you get here 1 minus 1 into cos minus 30 degrees. So I think you get this value also 1.34 per unit. That value also comes to be 1.34 per unit. Okay. Therefore, this QG2 value, you are going to get like 10 plus 1.34 means it is 11.34 per unit. QG2 value will come to be 11.34 per unit. 11.34 per unit. So I think all of you getting this? And how much is the reactive power drawn by this line? What is the reactive power loss in the line? That is the value Q1 plus Q2. Na? Q1 plus Q2. That's a Q loss. Q loss in the line is Q1 plus Q2. So it will be 1.34 plus 1.34. It will be 2.68. 2.68 per unit. 2.68 per unit. Okay, so these are various problems on the two-bus system. Without doing this whole calculations, can you tell the answer for this problem? Of course, by this calculations, you can come to know one of the option as your answer. I think it is C. What is the correct option? What's the correct option? Is it B or C? C is a correct option. You will come to know. You will come to know. But without doing these calculations, can you tell? Can you tell which option is correct? Can you tell which option is correct without doing these calculations? Is it possible? Okay. Look here, please. Look here. See, actually, by looking at this problem, we'll come to know one thing, that bus 1 voltage magnitude, bus 2 voltage magnitudes are equal. If both buses are having equal magnitudes, then definitely this bus will inject some reactive power into the line. This bus will also inject some reactive power into the line. Definitely. See, actually, from this bus, load is taking 5 per unit. And some more reactive power injected into the line means generator should supply a reactive power more than 5. Generator 1 should supply a reactive power more than 5. Are you understanding this statement? Both bus voltage magnitudes are equal. Bus 1 is delivering some reactive power into the line. This load is drawing 5 per unit. So some of these two should be supplied by generator 1. So the value of QG1 will be definitely more than 5. Definitely more than 5. Next, you see here. This load is taking 10. Definitely this bus will inject some reactive power into the line. Because voltage magnitudes are equal. So this generator 2 should supply a reactive power more than 10. So QG1 definitely more than 5. QG2 definitely more than 10. Like that, you can find only one option here, that is C. Only one option we are getting here is C. All of you getting this logic? But anyhow, that type of logic we have to use after solving the problem for a cross check. Yeah. So we'll stop at this point, the class. Tomorrow we'll be continuing with the long transmission line again. Long transmission line, particularly lossless long transmission line, I am going to discuss. Okay, till now, I discussed about different types of lines, two-bus system, power equations, and all in the steady state analysis. But we have to discuss little more about the long transmission line that we are going to take up in the tomorrow class as a heading of lossless long transmission line. That is very, very important with respect to GATE examination, which is an an important topic, which is an equivalent of the steady state power transfer equations. Okay, yeah. So if you have any doubts, so you can raise your hands now. If you have any doubts, you can raise your hands. Ajit.
Sir, my doubt is regarding this reactive power only here.
Okay, tell me.
Sir, in all the examples where we have discussed till now, we have considered the voltage magnitudes of the bus to be equal.
Okay.
So in the cases of unequal voltages also the same rules will apply, sir?
Means equal voltages. Bus voltages are unequal. At the time, you have to calculate reactive power and you have to decide it. You can't say both buses are delivering reactive power at the time.
So the same procedure like what you said, we stand at bus 1, we look at.
See, equations will be remain same.
Only the magnitude of voltage.
Numbers may change. Numbers may change. Equations, writing procedure will be same. Whether the voltages are equal or unequal, whatever it is.
Okay, sir. That's it, sir.
Okay. Bala Vignesh.
Sir, in today finding steady state power limit problem, two problem we have done, sir, with a short transmission line approximation.
Yeah.
Before that also we have done one problem. In first problem you take the approximate formula, but in second problem you take the exact formula. When we need to take approximate formula, when we need to take exact formula, sir?
Why you have taken approximate formula in the first case? Tell me your answer.
Sir, that's only I don't know why.
Yeah, why we have taken? I have written here. Just read it.
Because of neglection of series R and shunt admittance.
That's it.
Sir,
Neglecting them means your network is consisting only reactance. Series reactance.
Okay. Sir, and another doubt, sir. In real power flow, you said generally high X by R ratio it is applicable. How, sir? For why high X by R ratio it is applicable, sir?
For low X bar ratios, not only angles, voltage magnitudes may also decide sometimes.
Sorry, sir, can't understand. Once again, sir.
For low X bar ratio lines, not only angles, voltage magnitudes may also decide it.
Oh, okay, sir.
Sir, where the resistance is a dominant term, compared to reactance.
Yes, sir. Sir, in high X by R ratio, resistance will be low only, no, sir?
Yeah, low.
Okay, sir. At the time, losses will be lesser, sir.
Don't say about loss. Okay, losses will be less. That's anyhow, let's say. But you say resistance is negligibly small in comparison with reactance and power flow.
Yes, sir. Sir, another doubt, sir. In steady state, you said lumped model. We will do the calculation, sir. On Sunday, for long transmission line, we have found the exact distribution model, sir. Can we apply that in steady state, sir?
ABCD you can use, na?
Okay, sir. Similarly, that exact model for what we find in long transmission line, can we use it for short also, sir?
Yes.
Why? Because
I use for any length.
Why? Because I'm asking means steady state means we need to go with the exact model, but on the day for long transmission we found the distributed model, so that only I asked it, sir. It's lumped model, it's distributed model. How can we apply for steady state?
All of you, after we are getting ABCD parameters of long transmission line.
Okay, sir.
Those ABCD parameters you use in the equations of VS and IS.
Okay, sir.
That's
so we can
analysis only, na?
Oh, okay, sir. So we can use it in steady state also.
Steady state. But while you are doing load flow and all, I can't keep ABCD parameters in that.
Okay,
I have
sir.
to go with the model in the load flow.
Will it come in the upcoming class, sir? That
it will come in the upcoming class. See, by using that ABCD, you construct a pi model. What is that?
Okay, sir. Okay, sir.
Earlier, we have taken a network and we found the ABCD, na?
Yes, sir.
Now you know ABCD. By using that ABCD, you construct a model.
Okay, sir.
That model you use for a replacement of log line.
Okay, sir.
Yeah.
Thank you, sir.
Yeah. Muralidhar.
Hello.
Muralidhar, tell me. Diksha.
Yes, sir. Sir, in 167 slide, cost term in Q equation, cost term where we take, I am not understand.
Cost term where you will take at which bus, which equation you want to tell me, please?
I'm both three equation. I'm not understand cost
You
term.
tell me
where
one
we
equation. One equation. Tell me one equation first. Which equation you want me to take?
take. What, sir?
Which equation you want me to discuss?
Q2.
Okay. Which bus you are standing?
Second.
Second. So second bus is your reference.
Yes.
So V2 you should take as it is.
Yes.
Then V1, what you have to take? V1 cosine of angle gap.
Cosine angle from power flow.
Delta 1 minus delta 2 or delta 2 minus delta 1. That's your wish. Cosine of angle difference between the bus voltages we have to take for a multiplication of V1. That's the thing we said. V1 referred on to V2 here. V1 voltage referred on to V2 na.
Yes, sir.
If you are referring V1 on to V2, what you are getting? V1 cosine of delta 1 times delta 2. Why you are considering this? Because in my equation I got it. In the equation I got it.
Okay. Yes, sir.
Okay.
Yes, sir. Thank you, sir.
We are Avat. We are Raj. Priya? We have Raj?
Hello, sir.
Tell me Raj.
In 168 page,
Okay.
in this Q21 equation, the angle difference will be delta 2 minus delta 1.
That's your wish. Anything you can take inside cosine.
Cos term is
Inside you write delta 2 minus delta 1, delta 1 minus delta 1. But while you are writing the real power equation, you should be very careful to write what angle difference.
That's why I am asking that reference.
In case of real power, you take that concentration. In case of reactive power, you no need.
So the bus we are reference is bus 2, then difference will be delta 2 to delta.
You take it, no issue. You take delta 2 minus delta 1.
Okay.
Shiva,
Hello, sir. Good morning, sir.
good morning. Tell me, Shiva.
Sir, at 170, sir. 170.
170. Okay.
Sir, I don't get how you wrote the power flow directions here. Like
Power flow.
no reactive power flow. So here we have two bus voltages as say equal. Hence, we can say that like both reactive powers will be injected at both the buses.
That will
What
be
about
given
the
by
previous-
number, Shiva. Why you are bothering about it? You take some direction, calculate it.
No, sir, but if we take any direction, but like the net reactive power will be different, no, sir, for calculation.
No, Shiva. We are not dealing with numbers here.
Okay, sir.
We are dealing with notations.
Okay, sir.
Take the notations, calculate the thing. If it is coming positive, it is flowing in the direction what you have shown. If it is coming negative, it is flowing in the opposite direction. Yes or no?
Yes, sir. Sir, but could you please explain with an example, sir?
That's what we have done here. Now, Q2 injection we have taken. We have assumed in this direction, Q2.
Oh, we are assuming it.
We are assuming it.
Okay, sir.
Based on that assumption only, we have written the equation.
Okay, sir.
For example, Q2, if I have taken in the opposite direction, I might have written the equation on the basis of that direction.
Okay, sir. But the final result will be the same. Like if it is positive, then
It will be same. See, for example, after doing this calculation, Q2 you got negative.
yes, sir.
For example, if you have taken Q2 in the other direction, Q2 will make
Okay.
it positive at the end.
Okay, sir.
Okay, do it once again. Just change directions and do it.
Yes, sir.
Are you getting same result or not? Check.
Okay, sir. Then what about that real power direction, sir? Is it?
That's
same?
also your wish. That's also your wish. But
Okay, sir.
load it is taking real power.
Yes, sir.
I should show downward only this one.
Yes, sir.
But whatever P2 I have shown, that I can show into the bus or out from bus. That's my wish.
Okay, sir. Yes, sir.
Okay.
Yes, sir. Yes, sir. Got it, sir.
Yeah.
Thank you, sir.
Yeah. Gangadhar. Gangadhar Pawan.
Sir,
Tell me, Gangadhar.
slide number 159.
Okay.
After that, you have set one example, no, sir. After reference
Okay.
slides. Yes, sir. In this slide for bus 1, we are saying that V1 is delivering power Q, no, sir. Sir, but we have not considered any direction for that example, no, sir. That direction of Q. How can we say that it's delivering?
Okay. So you can show it. Bus 1 to bus 2, I might be taking the direction.
Yeah, sir. Then it will be delivering, no, sir. Okay, sir.
See, irrespective of this and all, what I was interested to tell here is, we have only one line here.
Okay, sir.
So I want to know whether the bus 1 is delivering Q or absorbing Q into the line.
But according to that
Listen, please.
Yes, sir.
So to check whether the bus 1 is delivering or absorbing, irrespective of direction of Q mentioned here, I should compare mod V1 and mod V2 cosine of angle.
Okay, sir.
Okay, I have done that comparison and I confirmed that bus 1 voltage magnitude is higher compared to bus 2. So this is delivering the reactive power
Okay, sir.
into the line. That commit we made. After that, I have shown that in the diagram.
Okay, sir. Okay, sir. But after this, you have told convention, no, sir, for saying reactive power. That we are considering the direction and then we are writing the equation, no, sir.
No, see, for example, in this 3-bus system, let's say, I am asking you whether bus 2 is delivering the reactive power into the line 2 to 3 or not. That's the question I have asked you.
Okay, sir.
Irrespective of this direction, just I have given this one. I am asking you whether bus 2 is delivering the reactive power into line 2 to 3 or not. That's the question.
Okay, sir.
Then what you have to do? First, you should take mod V2 value. Then you should take mod V3 refer dot to mod V2.
Yes, sir.
Okay, then compare these two. Then if
V.
mod V2 is greater, compared to that mod V3 cosine of angle, then I can say bus 2 is delivering reactive power into the line.
Okay, sir.
Else, if it is coming negative, I should say that bus 2 is absorbing the reactive power from this line.
Okay, sir. In that also, we are likely to use this convention, no, sir.
Which convention?
You are saying, no, sir, from which bus we are referring minus that opposite bus.
You have to use that convention definitely. And if you are standing at the bus 2, that convention you have to use, na. But
Okay,
direction will decide according to your view.
Okay, sir.
Will it be taken as V2 minus V3 cosine of angle or V3 cosine of angle minus V2? That is decided by you.
Okay, sir.
Any of V2 minus some number or some number minus V2 you have to take.
Yes, sir. I got it, sir. I got it.
Yeah. Any other doubts you have? Please raise your hands, else we can close the session.
1 minute, sir.
Tell me, Balvish.
Sir, that I didn't understand that how you relate that high X by R ratio in power flow, sir. Once again, please. Can you please?
So we have discussed about a lossless transmission line, right?
Yes, sir.
That's the reason I am saying you for high X by R ratio systems, we are going to get it.
No, sir. I'm asking. Before that high X by R ratio, you have written one statement that system is lossless. So that for indicating that you are mentioning that high X by R ratio, sir, because R is low, so system will be lost. Okay, sir.
Okay.
That's it. Thank you, sir.
Same.
Okay, sir.
Yes, sir.
Thank you, sir.
Good morning.
Same. Tell me, same.
Good morning, sir.
Good morning. Tell me.
Sir, I have a doubt on electrical machine that power flow equation in the EF and VT form.
EF and VT form.
Means field effect excitation and that VT will be the terminal voltage. That is V1,
Okay.
V2 like.
Okay.
Yeah. When we are considering generator, that IA current is the in some books IA is the reference current. Okay. Then the power flow equation is something like if we are deal with motor, then by considering the generator by reference to the generator, then IA will be negative minus of IA. Then here that the angle that will be del will be then greater than 90 degree. If I am considering that
actually strange. The current IA, to show that IA is negative in 2 ways, I can say.
Yes.
One, in the phasor diagram, showing that IA quite opposite.
Yes.
Other way is showing the direction itself is in opposite in diagram network. So in the network, they will show opposite direction for IA.
Yes.
But in phasor diagram, they will show that as a reference.
Okay. But when we means in the books, it is dealing with that considering minus IA.
dealing with minus IA. See, for example, this is your motor, let us say. Motor, and this is your VT bar, and this is E bar.
Yes.
Okay. So this is a direction of IA if you take. Okay, you will get some phasor diagram.
Yes.
For example, you have taken the IA in this direction only, but it is a negative value we have to show in the phasor diagram. And your KVL equation is getting disturbed, right?
Yes, sir.
So delta becoming more than 90 or less than 90, what is the reference for that?
Means I am considering the generator, but dealing with motor. Means
Listen, straight. Delta more than 90 degree, you say system is unstable.
Yes, sir.
Then less than 90 degrees stable. Then your
Yes.
question is that, sir, if I take this current in this direction only, negative IA, if I show in the phasor diagram, I am getting that angle delta more than 90 degree. The system is unstable. That's your doubt. Is it so?
Yes. Then how the power flow equation will
Listen. Delta is measured between what?
measure it? That is V1 and V2. That is different.
That angle you should consider, na? Why you are bothering about current angle now?
Okay.
Even though you take current in this direction, ultimately after drawing phasor diagram, you should check the angle gap between VT bar and EF bar.
Yes.
That will decide the system stability.
Means don't go for complexity directly. Means
Don't go for complexity. You take this current in the same direction of motor, means into the motor you take, and you take that itself as your reference if you want, and you show VT bar, EF bar by using KVL.
Yes.
Okay.
But I can also write by opposing the current direction actually. Also,
In
that
opposite
is
direction, what, right?
if IA is opposite direction, that also I have to write another KVL equation. Means in the
KVL equation will be different, right? At the time. KVL equation
Then,
for this direction, VT bar equals to EF bar plus IA into ZS.
Then sir, if we are taking someone is 0, someone is del, then del will be surely greater than 90 degree from the equation.
It may not be, Swain.
May not be.
May not be. No.
Okay.
Ultimately, after drawing phasor diagram, this gap only you have to check, right? See, for example, IA, I am showing like this first. Okay.
Yes.
VT bar is something like this. Okay.
Yes.
But this IA is going into the motor. For this VT, from this VT, we should subtract IA into ZS.
IA into ZS, yes.
VT bar equals to EF bar plus IA bar into ZS bar.
Yes, sir.
Okay, so from that you should subtract IA into JXS. So that IA into JXS will be in the downward direction because it is negative.
Yes.
So this is your EF, na? EF, and this is your delta angle.
Okay.
Now what you want to do? You want to take IA in opposite direction.
Means minus IA.
I will show that in black. This is minus IA. Okay, so it is IA out. Outward. Now where is your VT?
VT is
in this direction only, right? VT will be same, na?
VT will be same.
Then EF, how you are going to get EF?
Then same sir, direction. In our mind.
Same direction.
But in our mind, means our mind is concerned with that.
At the time, Swain, the angle difference between this VT bar and IA bar will not fall in the range of 90 degree.
Okay.
You see this angle. This is very high, na? It will be more than 90 degree, right?
Yes. Sir, then when we are dealing with that, means in our mind we have to concern that VT will be at greater than 90 degree. Means in
greater.
our mind, in our mind.
Yeah, that we should say in our mind, exactly.
Actually, I am asking you my confusion in my mind. What are my confusions in my mind? I am asking to you that question.
For example, if you have taken VT somewhere here, not more than
Yes.
90 degrees, somewhere here, then it may act
Yes.
as a generator only.
Then
That
again,
machine
okay.
is going to act as a generator only at that time. So no.
Means IA out, if we will consider for a motor in negative, then that angle will be greater than
Yes.
90 degree.
90.
Means it is in our mind also.
Yeah, we have to think that in our mind. Thinking that as a motor. Already you said it's a motor, right?
Okay. Thank you.
Okay.
Thank you, sir.
Any more doubts? Nobody's having. So I'm closing the session. Thank you.